talk is really about rethinking a lot of the ways that we approach scale and distributed systems. So just for Alexi, I just wanted to really bring out the entire topic of scale. I'm not really going to be talking about Scala in this because it's kind of a keynote. It's very theoretical talk, bringing in a lot of new ideas. And I kind of constructed this talk because we all work in, and I'm sorry, I'm kind of small, you may not be able to see me, but we all work in really different areas on different domains and have different problems to solve. But my hope with this talk is it brings each of you, ideas are triggered by it and specifically to your own experiences. And I'd be really interested if you have some ideas or things you want to talk about, please come up and find me throughout the conference. I'm here all today and tomorrow. All right, so let's roll. So you can find me where I work now and have on LinkedIn. I didn't really want to list it. But at the moment, I'm also a committer on PhiloDB, which my colleague Evan Chan is going to be talking about later in the conference, I think later today. So I've contributed to a lot of different open source projects. I've spoken at a lot of big data and Scala conferences, but everything I've done in the last 8 or 9 years has been in Scala. And so everything I'm talking about is kind of coming from things that, like ideas based on experiences rolling Scala-based applications and infrastructure into production at large scale. And so primarily this talk is about concepts in complex adapted systems and how do they apply to distributed systems, and how biological systems innately solve things like distribution, regrowth, and rebalancing. And also the possibility of new approaches to building intelligent adaptive systems that are resilient, because these are things that for any of us that deal with, I don't think it's just even infrastructure, but any of our systems have to be able to be resilient and survive, be fault tolerant, and this is just a really repetitive pattern I've found over what we do over the years. And so the foundation of this talk is based on, before I started working in tech, I was doing a lot of scientific research in biology in different areas, but it kind of centered around finding better ways to handle system dynamics and thinking about how could we re-engineer entropy in systems at a very high level. I don't really want to get into it, but also this talk was also triggered by things that I've experienced in this industry over the last 18 years, and particularly the last decade. And then starting to question how we approach these problems of distributed systems and scale, particularly at scale. And this is really the underlying idea and question. Problems cannot be solved with the same mindset that created them. So there are problems that we have to solve, and I'm not the only one, I'm sure, but we run into them, some version of them over and over again. But primarily we approach these problems from a computer science point of view. And what I wanted to bring up in this talk is that there are many other scientific approaches that kind of overlay and could possibly lend ideas to this, and it's very hard, and I talk about this at the end. We're all on some kind of assembly line if we're not in research, trying to deliver products, and we have timelines, and we have other teams that need things from us. And so it's very difficult to step off that typical computer science approach and try and solve the bigger problems. And that's something I'll talk about at the end. But what I find really interesting is that if you look at other scientific disciplines, their technologies are advancing quite rapidly. So that's an important point to consider. So when we're trying to design and build intelligent systems, we could define AI as systems that exhibit intelligence, and ML as systems that learn to be intelligent. But we often approach systems to have some kind of governing or orchestrating awareness outside of the nodes specifically and outside of the running applications that we're deploying. And since this is all about also scale, from my experience, it all comes down to data. It all comes down to information that we're trying to pass around in these systems, information that we're gathering, information that we're transporting, how are we storing it, where are we storing it, what's the replication, what's the compression, what algorithms are we using when we're doing query patterns. And what I kind of wonder, and I have a lot of questions in this talk to the audience to think about, are we possibly missing some kind of common intelligence substrate? Because we keep, at every company, at every project we move to, every job, we keep having to solve some version, like I said before, of the same problems. And I just wonder if there's some way, and like I said, there's really no time to do it unless you're in research, I think. But is there something that we could have? And I don't mean some kind of governing thing like Mesos or Kubernetes or anything. I mean something that actually we're going to talk about in just a few more slides. But something embedded in the system. So just for a basic slide about what we're talking about with systems, to be clear, we're talking about systems that are comprised. Systems are entities in and of themselves. They're usually in a larger system. They're usually comprised of subsystems, and those subsystems are comprised of entities. And also you have to look, when you're looking at these systems, we're talking about what are the interdependencies with all of the entities and how are they affecting each other. And systems theory is it's been around for a while, of course, but it's a really interesting way of thinking because it's an interdisciplinary study of systems. And it's all about, it's coming out of engineering originally, and it's about discovering how elements of the system and their subsystems interact to produce given states. And changing one part affects other parts in the system. These are all principles that we're very familiar with. But what's interesting to me is that out of systems theory, there was a biologist in the late 60s, Ludwig von, I'm probably pronouncing his name wrong, Bertalanffy. And he proposed the idea of general systems theory because he felt that the scientific investigation needed something, even from the technical layer that system theory was coming from, needed something more general, something that could apply to sort of the more unified paradigms of investigation and thought, transcending just the technical problems. And then from that, and by the way, his book is excellent, General System Theory. It's funny how here's this book written in the late 60s, and a lot of the ideas still apply today because he was coming from a time when things were rapidly developing, and this is, I think, the same kind of situation. And what's interesting coming out of that now, that's leveraged more and more is complex adaptive systems theory, and I'm going to say a scary word now, complexity theory. Complexity is something that, I've given talks on in the last few years about how to stave off complexity and how to simplify systems in your architectures and things like analytics pipelines. And so it's kind of ironic that I'm talking about complexity now. But I want us to think about complexity in a different way than we've thought about it, than the way that the context that we think about it now. Because right now complexity is, in one hand, something to be avoided in what we do at scale because it makes things incredibly difficult. But the other way that another way of thinking about it is something I want to introduce, which isn't new, just from another scientific discipline. But what's interesting about complex adaptive systems theory is it stems from system theory. It takes into nonlinear systems, chaos theory, game theory, so a lot of different ways of thinking that apply to not just computer science and distributed systems, but many other ways of thought. And in distributed systems, what we all find, of course, is that the larger the scale, the greater, the more moving parts, the more things that can fail. And they can be tremendous failures when you get into large systems, particularly with a lot of data. But what's interesting is, in comparison to that, is in biological systems, the greater the complexity, the greater the overall stability and resilience of the systems. And that's really something that I want us to look at. Like, if we could just put aside our a fear of complexity in distributed systems and what we're deploying and running, and just possibly take a look at if we could consider complexity in a different way and possibly apply it in a different way. A really interesting application of is the butterfly effect, and we see this, it's used heavily in weather prediction, but it's all about how a very small change in initial conditions, like such as a rounding error in your calculations, can steadily amplify to dominate a solution, causing extremely different outcomes. So in weather prediction, initial conditions are very rarely known. And in computer science, of course, we can see something like the butterfly effect with cascading failures when bugs are introduced, and we see a ripple effect throughout our systems. And from that came ensemble forecasting, and this is also used in weather prediction, but where you have a range of possible future states. So instead of making a single forecast, and this is something that we do when we're building new systems or architecting new systems with our teammates, a single forecast of the most likely outcome, you instead do an ensemble of predictions produced. So like when we're looking at our own systems and building them, we can pretty easily, as opposed to other types of scientific disciplines, we can pretty easily list out the things that could possibly happen. They're not these great unknowns or anything. But we never know exactly when they're going to occur, any of those failure scenarios. And it's heavily used also in wildfire prediction, because wildfire prediction is highly unpredictable situations. So from a human and an animal perspective, fire is a very destructive force, of course. But if you look at it from a different point of view, and that's what this talk is more about, like if we shift how we're approaching things, fire is actually, it's destructive, but it's also a transformative force. You're moving from one state of energy to another state of energy. And not only that, but you're also moving from some kind of state that goes down to the kind of ground zero. And then what comes out of that is a completely new system, completely new entities in that system that are growing, that can be more diverse, et cetera. And they're much more robust. So I want to step back also, and when you start to talk about a lot of this, I really wanted to add a little bit about entropy, events, and time. Particularly for those of us that are working on problems around time series. Entropy is often for computer science talked about in the sense of information entropy. So the basic idea of the second law of thermodynamics is the law of physics stating that entropy increases. And we're going to challenge this as we move into another scientific discipline in a few minutes. It measures the degree of disorder from a system, and the increase in entropy accounts for the irreversibility of natural processes and the asymmetry between future and past. And we're going to question that in a second. Entropy and the arrow of time. So here's a pop quiz. Who's in physics here? Physics background. Okay. So if given a complete knowledge of the universe for two instances of time, how would you solve which instance happened first? Order, disorder. Alexi. Calculate the entropy between the two snapshots. The one with the lower entropy was first. So in the wild, how would you might in distributed systems be checking, with your storage, reading something about your metadata, but being able to calculate the entropy of the two snapshots without any of that information. If you could have that awareness of comparison, you can do that as well. And it's very interesting that when you look at biological systems, this arrow can actually reverse. But in physics, it's a given that it doesn't. Future light cone, so I had to add a quote by Stephen Hawking. If the sun were to cease to shine at this very moment, it would not affect things on Earth at the present time, because they would be in the elsewhere of the event when the sun went out. I can see better now. So what the future light cone is, it describes really heavily what we deal with, I think, dealing with events and distributed systems. If you throw a stone into a pond, it slowly starts to ripple out. And so the light cone is kind of like from that genesis event. If you sort of layered that ripple of time over each other, it becomes a cone. And so from the sun at one point, at that genesis point, it ripples out. It takes 8 minutes or something for light to actually get to the Earth. And we deal with this with events all the time. So something comes to our cluster, the first node is aware of it. Something says, so if you ask that entity, that node in the cluster, did this occur? That first entity can say, well, yeah, of course it occurred. But if you ask other entities that haven't, received that information yet, they could say false. I don't even know what you're talking about. And so that's sort of the future light cone applied to what we do. And you can think of that as, I have a really nerdy shirt that says a long time ago, but somehow in the future, but it's really applicable. Events lie in the future light cone everywhere. So all of the events that we're gathering, storing, processing, analyzing, compressing, all of that, we're just constantly looking at the past. And this is a really interesting idea. Time is a derivative of events. Events occurring in time as derivative events, where there's a sequence of things happening in time, or what people are starting to talk about more and more with quantum physics is pretty fascinating, where time is just a sequence of events, where time comes out of it and time is just another coordinate. Maybe it's more accurate to say that time flows as events happen, and the flowing of time or passage of time is events, by Anthony Aguirre, who's a physicist. And so then, given all of that, how do we rationalize what now actually is? So we could think about now as the moment in time that has just been created in the expansion of the universe. And it's just time moves forward in the continual creation of nows. So let's get into biological systems. Building intelligent, adaptive, self-organizing systems. And I wanted to start with talking about viruses, because viruses are pretty fascinating. And viruses also exhibit, if you look at them and compare in relation to, for example, humans, but many other life forms, they adapt, they co-evolve, and it's pretty fascinating how they do it. And if you can imagine our systems that we build and deploy being able to do something like that without some outside governing body, that would be pretty amazing. We're going to go into that a little bit. But viruses themselves are highly adaptive. They mutate often, and they interrelate with the immune system of their host, where the host is constantly adapting to the adaptations and the mutations that are happening in the viruses themselves. And viruses have all these different strategies. They have things like mimicry, to look like the structures in their host cells. They have evasion tactics. They have suppression, so they can suppress the behaviors that the body and the immune system would recognize them as what they actually are, to actually kill them off. So they're constantly evolving strategies that allow them to survive longer and be passed on in the genetic or the virome from one organism, one host to another. And the immune system of the host is constantly adapting along with it. So if you think about, how could we apply this to the systems that we're building, it's pretty fascinating. Obviously, it's hard to do, when you have, tickets and deadlines of something that has to be deployed. But I just wanted you guys to have something to think about throughout the conference. And please ping me if you have more ideas about this. So the immune system itself is really interesting, fascinating. It exhibits a highly distributed, adaptive, and self-organizing behavior. It's self-programming, it's self-learning. All of these between the immune system and the viruses are doing self-programming in runtime, basically. And another thing that's interesting to look at, we see things like the domino effect, where one event can trigger changes in others. So I wanted to start looking at more complicated biological systems in comparison to the distributed systems at scale that we build. This one is really interesting, evolution and complexity at the edge. And the edge is sort of like that edge of chaos where things can start to, crazy things start to happen. And this is about the proliferation of species at the transition between land and sea, where there's thriving transition zones. And the way that these complex and biodiverse systems evolve is kind of through a domino effect. So you have a system where you have abiotic conditions, and you could think of that as some kind of substrate. We have like our mesoslayer or whatever, some foundational system that we deploy to. But once lower, sort of simpler forms of life come, like simple cells and other lower level simple resources. And then slowly what starts to happen is the chain, sort of the pyramid of what needs what and what relies on what and what the dependencies are, they slowly start to build up. And what you get at the end, and what this slide is talking about, is how it's not so much about the complexity, but about the resilience with this biodiverse system, and how how they develop at the edge because of the diversity and the richness of their environment and what's happening. And I think about things like this in the sense that, you know, I deal a lot with building out and thinking about fault tolerance and making things self-healing in large systems. And there's a lot of strategies here that I think are applicable, but, you know, difficult to solve and how to build it. And the idea I'm trying to propose is we shouldn't have to keep facing these problems every project we start and every company we go to. I just wonder if there's some overarching collaborative thing that we could all contribute to where we have this kind of substrate to our systems. So self-organization is something really interesting that we don't really get into for more architectural reasons with distributed systems. So we tend to assume that organization and order need to be imposed by some external force. Individuals can be acting and reacting to each other, and complex organizations like schools of fish, swarms of birds, ant colonies, traffic, manage to organize themselves into emergent patterns. One sec. Another kind of self-organization is peer-to-peer. That's something that we do deal with, of course, in computer science, but this is peer-to-peer organization where there's no governing body outside of these musk oxen. They live in the Arctic, but when they're in danger, they create a circle among themselves. They're not like, you know, talking, but they're communicating to each other, and they form a circle around their young, basically. Self-organization and emergent patterns with schooling, swarming, and herding that you find naturally in larger groups of animals. So fish, in this sense, can sense and keep a distance from their nearest neighbor. And if you've ever seen this, they move incredibly fast, and there are large groups of fish. And how are they? They're actually sensing, and they have input biological feedback machines to receive and process the sensory input. And you know, this just makes me think of, you know, I'm deploying nodes, huge clusters with tons of nodes and many data centers, you know, over tons of racks. And wouldn't it be, there's some concept there that I think that we need to think about, being able to take this self-awareness and self-organization where we don't have to always rely on something outside. There should be some base intelligence in there. And the problem with this is, of course, in computer science, we're always talking about separation of concerns, where there should just be this one thing, and also keeping things simple. It should know one thing, do one thing. So it's sort of this, you know, like fight between how to keep something simple for operational reasons and reasoning about something, but also trying to make things more intelligent and possibly a different way. So emergence, I just have this slide about looking at ant colonies, which is really interesting. They have a very limited set of instructions, but they're able to self-organize in situations where they're exhibiting complex structures and behavior, far exceeding their intelligence and capability alone. And it's a decentralized structure to self-organizing. And all parts are contributing equally. And when you think about economies of scale, systems comprised of many actors making decisions in parallel, and they share that information amongst each other, but it's all happening, you know, at the same time, and they're moving around, and each entity or each actor in the system is influencing the other. So when we think about cyclic patterns and resilience, resilience is something I want to get into now. There's something that I call the 3 R's: replication, regeneration, and rebalance. This is something that biological systems do natively, but it's something that we have to think about and construct in our systems. Self-organizing patterns, there's a lot of these in terms of movement. And there's a lot of different type of movements in systems. And a lot of that has to do, or it all has to do with resources and what's affecting the systems that those organisms live in, or those groups live in, or nodes. So for migration, birds traveling in a pattern, a V pattern, this is really interesting, the annual pattern of movement of Arctic tern. They actually go almost from pole to pole in every single year, and they're these pretty small birds, but they have the ability to navigate, and it's the longest migration on Earth. And then there's daily patterns of movement, and both of these are predictable. And that's the other thing to think about, is all of these movements, all of these behaviors. There's to emergent behavior and self-organization, it's very difficult to predict, but more easy to program. But some of these movements and migrations, they're much more easy to predict, and I'll mention why in a second. But the daily movement of, for example, Arctic wolves through their territories might be anywhere from 40 to 100 miles per day. And they're organizing themselves to move through their territories to find food resources, basically. And all of this is dictated through seasons. It's all, you have these systems, and outside of that system is a larger governing force. It's not a governing force, it's abiotic factors that influence the systems themselves. And then outside of that, because what's affecting, what's actually causing the seasons is planetary orbit and axial tilt. And that's a system that's in another system, in another system. So it's pretty fascinating to think about all of this. But that's what we're really trying to do. And that's actually what we're facing when we're trying to design with groups of people, sitting down and discussing how are we going to build this new system? What is going, what's the scale of this going to be? What are going to be the things that we have to handle? What's going to be affecting this? What are we going to have to survive? All of these things, I think, are relative and applicable. So for resilient systems and diversity, there's a high degree of diversity between elements, where it's more robust as a variety between elements, making them more effective at absorbing change. So the more diverse a system is, the more robust that system is. And that kind of ties into the idea of in distributed systems or computer science, we have roles, different roles of behavior in our clusters. And in ecosystems, we have what we call niches. And it's the same kind of thing. What do these particular types do? What's their function? What's their role in the system? I think I'm talking too fast. Just looked at my time. So when we try to pick out anything by itself, we find it hitched to everything else in the universe. That's what this next section is about. Everything affects everything that's around it. And there's a theme about that related to autonomy that I keep hearing in conference talks. Everyone's talking about autonomy. And it's funny because I find that I can argue of something being autonomous and something that should be autonomous. But then when you really think about that thing, nothing is autonomous. I mean, everything relies on something. Usually many things. So it's kind of an interesting point. Trophic cascades are something that I think we see in distributed systems, in our behaviors of our systems, as well as very much so in biological systems, and also in cosmology. But it's talking about a process which starts at the top of the system or meta-system hierarchy, eventually affecting all the way down to the base. And it's a matter, and this is a question for you guys because I'm going to ask what you think about it after. It is a matter of common experience that disorder will tend to increase if things are left to themselves. Now that's pretty true if you just think about physics from that particular approach or many other scientific approaches. And that's a quote by Stephen Hawking. Now I just wanted to show you a pretty classic case study. It took place in Yellowstone National Park. They didn't set out for this to be a case study, but it emerged as something that really exhibits some very interesting behaviors to look at. So Yellowstone is a complex system in constant change, a very complex system, and we deal with complex systems. So I wanted to use it as an example. In these systems, well, in 1926, little history, the last wolf in Yellowstone National Park in the United States was eliminated. And by 1994, the elk population, which was the largest, I guess, ungulate population, herbivore, that population grew out of control. It grew to roughly 19,000 entities in that system. In that system, wolves are what we call the apex predator. They're at the top of that food chain. And what people didn't quite realize at the time was the effect in a system when you take something like this extremely regulatory role on all the entities out of that system, how it just cascades through the entire system itself, what actually happens. So think about the systems that you're writing and you're deploying and how we could possibly think about this and apply it. So elimination of the wolves caused a cascade of changes throughout the entire ecosystem. With no natural predator, the elk consumed most of their food resources. Not really shocking. But they didn't really understand, and they didn't expect the extent to which that happened. And what proceeded from there over several decades was large-scale destabilization of the system. And again, think about the slide where I was talking about diversity and diversification in systems and the innate resilience that it brings. So with the absence of the top predator, the elk increased. The food sources for all the other top mammals like bear, which grew to an endangered species level because of all of this. Their food source slowly disappeared because the elk were eating it. You know, you can think about all these different roles in our systems that we deploy where something taking over more resources than you wanted it to because there's something else missing and they can come in and utilize all of that. The coyote population increased partially to fill an open niche that existed where the wolves were. And then what's really interesting, I think, is the tree and plant height and the numbers decreased dramatically, and that affected sort of the smaller animals and different roles in this system. And so after a certain number of years, in 1995, they decided to introduce 14 gray wolves from Canada back into Yellowstone after being absent. So 60 years, the system just degraded and destabilized without this particular role in the system. So after later on, after the first 14, they introduced 17 more wolves. And by December 2001, their population had grown to 132. And what happened was really interesting. In the system, there was adaptation and predatory pressure behavior was exhibited. So because the predatory pressure from the wolves keeps the elk on the move, the elk before were using up all the resources in the particular zones that they were in. And so that there were no more in those areas, and they continued to overuse and use up all of the resources in those particular systems that they were moving through. And so with the reintroduction of them, the elk actually adapted. They had to readapt to learn that they couldn't just stick around in particular places and use up all of those resources. They realized they had to move around to be detected less by the predator. So it affected resource balance throughout the systems, because Yellowstone is actually a very complex system, but it's surrounded by other systems where all of these resources and all of these entities go back and forth throughout. And then what happened was large-scale regeneration in the system. So the elk started to avoid parts of the park where they were more exposed to the wolves. The forest and the aspen and the willow began to grow back. All of the diversity slowly started to creep back into the system, and then eventually it started to get repopulated, and the whole biodiversity of the system began to come back. Many different unrelated animals that use up different resources, they all started to come back, and all of those affected all of the other ones. And so all of a sudden you have this system that becomes slowly more complex, but it's slowly becoming, after they destabilized it, it slowly becomes more and more resilient. And you can think about it as becoming more complex, but I don't think that it's the complexity that we think about in computer science. I think it's a different kind of resilience complexity where something is able to be more like a self-adapted and self-healing systems. Large mammal populations rebalance, and this is necessary with all of the smaller subsystems. The Yellowstone grizzly bear, which were marked as endangered, came back, and everything started to rebalance. Erosion, this is really neat, the actual topology of the entire area, the system itself and all of the systems around it started to change. The river shapes started to change, water started to pool up, like beaver came in, just like completely changed what this entire system looked like, and it made it incredibly resilient again on its own. So one roll can change the entire topology of a system, and I think that that's a really powerful idea. I can't really stand up here yet and describe, how we can apply it, but I think if we all kind of think about this, ruminate over it, and please contact me, Twitter, or walk up, during the conference. I think that this is a really powerful idea for us. So self-balancing systems, again, Stephen Hawking quote, "It is a matter of common experience that disorder will tend to increase if things are left to themselves." So given the case study that I just reviewed, what do you guys think? I mean, this is something that they removed a top rule, and then on its own, when they reintroduced it, the system became more balanced. It went from kind of disorder back to a natural order without anything except just reintroducing that rule. So you have to ask, was Stephen Hawking right? Which is a ridiculous question, of course. I just wanted to ask it. So innovation, it's really hard, I think, for us to take ideas like this, and I mentioned this a little bit before, but to step off our kind of assembly lines of timelines of when things are due, tickets and project deliveries, and something that other product teams need, or things like that, or things that have to be deployed to your customers. So the assembly line versus those of us that are lucky enough to be in research situations, it's a very different criteria that we're working under, and so it's very difficult to sort of step off and be able to think of things in a larger sense differently. There was a time, though, when companies would fund and sponsor a lot of their scientists internally, or engineers, and some of them have won Nobel Prizes, like back a long time ago, Sony and IBM and Bell Labs. But I think we find this less and less. Research and development has become less R and more D, and this is a quote by Professor Ashish Arora, Economics of Technology and Technical Change. And two last things I wanted to leave you with. The rate of innovation, I find it really interesting, back to one of my first two slides, where I talked about how we're really approaching a lot of these problems, and given the fact that we have a lot of constraints, and there's a reason why, but we're approaching a lot of these problems in purely a computer science approach, and in that kind of mindset. And I wonder if we could think into these larger scientific disciplines and apply them, if that would help us with our, not so much speed of innovation, because I'm not trying to say that we're not innovative, but just as a community, as our particular area of the industry, could we speed that up possibly by taking a larger view of things? And I bring that up only because when you look at some of the other scientific disciplines and their technologies and how rapidly they've been evolving and where they've gotten to, it does make me wonder if there's something that we're missing, if it's more important to sort of press our employers and our companies to say, hey, we need to stop and think about this and solve this problem, like actually solve it. And so building on that, I just wanted to say, be more experimental. I've been in many situations over the years where, because we can, predict, we can, list off in a new project all the ways something might fail. But if you spend too much time doing, assumption planning, then that's a lot of upfront time that you're not getting your stuff out there and not actually looking at its behavior in the wild and testing it in different ways. So I think that that's a really important step to take, to just get your shit out there, see how it behaves, and get some actual data. Huge discoveries are really the result of giant collaborations. And this I love because it's from one of the 2017 Nobel laureates in physics. And I think that that's one of the most wonderful things about our community. For those of you that are new to the Scholar community, I think this is one of the most amazing communities. I've been part of it for at least 8 years. And I really think in terms of that, but also in the larger open source communities, it's so important that we still remain exchanging ideas and working together and trying to build things together and solving larger problems together. And it is difficult because those of us that work at companies, when we can't share things, but we want to, you know, hopefully over time, I think that might be starting, actually, I think that is starting to change. So we might be seeing a resurgence cycling back to being able to do that as engineers and as a community. So, thank you.